I'll just continue right away. What does periodicity have to do with string matching? It was a notion defined on strings, but it doesn't seem to help us with string matching much. We'll get there. First of all, assume we have a string. No, I called it P again because it will be our pattern in string matching. And assume we have a P that is not a period. So it's some number, and we know it's not a period. OK, one more time the picture. What does that mean? We aligned the two strings. It's the same string. We shifted it by some number P. But it's not a period, so it means at some point, or maybe many points, there's a mismatch. Otherwise, it would be a period. So that means we can find a position. I called that position omega, so we can pick this one. Yeah, it's actually down here. We can find a position that testifies against this periodicity. So we find a witness that shows that if I compare this character at that position with the one up here, that's omega plus P, there's a mismatch. OK. Again, the question, why does that help with string matching? We'll get there. The next observation is if you have this situation, you have a non-period and you have a witness against periodicity. Now, if I also have a text, maybe again a picture for that, I have a position I in the text and the position I plus P. So our P, the non-period. Then at most one of them can be the beginning of a match of P. So if it was a match of P, we could put P here and that would all be the same, or we could put P here and it will all be the same. Now what I'm claiming here is it's not possible that both are. We need a longer pattern, I think. It's not possible that both are matches. Well, just assume they were both matches. So all the characters here between the text and the patterns were the same. Well, that would in particular mean that those are the same. But hey, then we would have a period in P. And we assume there is no period in P. So that can't be. And in particular, if we have a non-period, we have our witness, omega, somewhere here, that tells us the positions in the text at the character at that position is different. So also, these here are different, and whatever's in the text, it can be one of those two, but it can't be both. So it can only be one of the two characters. So only one of the two positions can possibly be a match. We don't know whether it's a match. It could also be that both are not a match. But not both can be matches. Well, and that helps for string matching, because string matching is all about disproving guesses, disproving that certain positions are the beginning of a match. And well, we can formulate this as a duel between two positions. We have these positions I and I plus P. And if we compare the witness positions with the text, that eliminates one of those two guesses. So it's a duel, and one dies for sure. The other person might survive or not. For now, we call it the winner of the duel. It's not clear if that's a match, but it's the only that might be a match. All right? And what we do is essentially this comparison here. We take the two positions, we take this position in the text, I plus p plus omega, and then we compare this position with the two positions in the pattern, and that eliminates one of the two. We can turn this into a string matching algorithm as follows. And for all that follows, I assume that the pattern is aperiodic in the sense we defined it in the last section, which means the period is the smallest period is at least p half. Okay, I should say smallest period. And we won't discuss the case if the pattern is periodic. That requires slightly different tricks. They're not necessarily more complicated, but this is the one that has novel insight, so I want to present it to you. Whereas we won't make it to a full parallel algorithm in all the details. That would lead us too far. So if p is aperiodic, we define this this number that's just an abbreviation. That's essentially the bound on the period, and we round down to get an integral number. And that will be a block size. But before we do blocks, we compute based on our pattern, so that's a pre-processing. We compute witnesses against periodicity. And here, because the smallest period is, well, at least this mu, for all the smaller numbers, the numbers 1 up to mu, those numbers are non-periods. They're not periods. That means there's a witness against this periodicity. And this is what we compute here. So omega I is witness against period I in P. I should have said that somewhere, but we're pre-processing the pattern. So we compute all those witnesses, and we'll briefly talk about how in a second. But once we have those, we define the blocks of our text, blocks of size mu. So we take the first mu characters, the next mu characters, and so on. That's all these. And inside each of the blocks, we run duels. So there's, in each block, there's mu different guesses, mu different potential positions where a pattern might start. But I also know this is in a small neighborhood, so I can cover all those whenever I take inside a block 2 positions. So that's 0 up to mu. Whenever I take 2 positions here, their distance is less than mu, so their distance is a non-period. So I can find a witness for this non-period, and I actually pre-computed it. It's omega of I. And by comparing the text character at those positions with the pattern, I can eliminate one of those 2 positions. Okay? And that means once I've done, I'll show you how the duels are done. Maybe I'll show you first how the duels are done. So just look at this picture. I wish we had that on the previous slide. If your block size, if mu is 8, you would have 8 different positions inside this block that could be potential matches. And now you play this tournament of duels. In each round, one of the 2 is definitely eliminated, because we find a position in the pattern that mismatches the corresponding position in the text. So in each round, there's a winner of the duel that's passed up the tree. So it's like a football tournament. Always the winner goes on to the next match. And in the grand final, there's only 2 left, and the winner will be, well, the only candidate for a match. Okay. So this is what we do in step 3. We do this binary tree of duels until we have a single potential position left for a match. We still don't know whether that's a match. That's why in the last step, we check all those naively. Now the trick here is, this sounds like checking naively, sounds like you would have to spend theta m time in parallel again. For this slide, I don't care because it's sequential, but you can already think about how to do that in a better way. But let's briefly stay in the sequential setting and analyze how long this takes. Well, the first step is easy. It's just a computation of one number. We can do that on all processors or just one. OK, sequential, sorry. So just constant time to compute that. Then we have to compute all those witnesses against periodicity. I'll tell you in a second that it is essentially, again, our good old friend, the failure function. We've already seen that periods are very related to those failure links, so it's probably not very surprising that you can use similar tricks to also compute those witnesses. Again, we won't go into details of this part of this step 2. In a vague sense, you can say like KMP, but that's glossing over details. Now the third step, you have mu inside each block, so that's the number of duels you have to play. And mu is essentially theta of m. And the number of blocks is n divided by mu, so that's n over m. In the sequential setting, you would do those one after the other. But that's n divided m times m, that's theta n. OK? And then the last step, again, sequentially, we just, for each of those positions, do our m checks with the characters. And if we found a match, we report it. If not, we don't. Again, in total, theta m time. If you add this all up, it's another theta n plus m worst case optimal string matching method, essentially like KMP. But that was sequential, and we already had one that worked well, and we still haven't discussed this step 2. So the real benefit of this matching by duels is if we go to the parallel setting. I don't know if you could see this. The code, it got a little smaller because I had to squeeze more on the slides. But apart from that, the code is actually the very same thing. But for each of the steps, we have to think about how to do it in parallel now. We don't have to worry about the first step. We do have to worry about the second step, but we will skip that part. It turns out that this is fairly complicated. But people have found clever ways how to do this in parallel logarithm square time. So again, the details are beyond the scope of the class. We want to discuss how to do the other steps in parallel, though. Step number 3 is actually fairly easy. All the blocks can be handled independently, so we can assign those to different processors. That's easy. Now we have to play roughly m duels in each of those blocks. If we were to do that well, just with one processor sequentially, we would be back to our theta m. That wouldn't help us. But we have this tournament of duels, and we can play all those duels that are on the same level independently, because they don't involve, well, the only dependencies we introduce is that for this duel to be played, we have to know the winners of the child duels. But if you're staying on the same level, no such dependency exists. So we apply all the duels on one level and then move up in time level by level. So the height of the tree is our parallel time. Haven't we seen that somewhere before? That's almost the same as for the sequential prefix sums. We started out with this summation tree that's just a linear list, and then we transformed it into the balanced tree and noted we could move up level by level, and that way get height of the tree as parallel time. And in the same way, well, we could, for prefix sums, do blocking to keep the work down, but well, the same tricks work here. So as for the prefix sums, we can do this, and that gives us log of mu rounds, and mu is roughly m. So that would be log m parallel time for step 3. The last thing is step 4. So I already said we cannot afford to check a single guess sequentially. But we don't have to. Actually, checking a single guess is also embarrassingly parallel. You could check every little, every character match between the pattern and the text independently, but you have to combine the results. A pattern matches a certain substring of the text if all the characters match. That's an and between. Do the first two match? Do the second two match? The third two match? So you can compute the matching results on in parallel on different processors, but then you have to compute the and of all the results. Okay, is there still space on my slide to squeeze that in? Maybe up here. So it matches if the first position matches and the next, and so on and so forth. So what you have to do is compute in parallel the and of a number of bits. And you'll discuss this in the tutorials in a little more detail. But you can do it essentially like the prefix sums. In the tutorials you will see you can somehow be even smarter for this special case on special PRAMs. But we can always do prefix sum style log m time by using that and as an associative operation. I made that remark back then. You can replace the sum by any operation that's associative, and is one such. All right. So that was theta log m time for the step 3, and also theta log m time for each of the guesses. And we can do all the guesses in parallel. So it's also for this one, theta log m time in parallel. Okay, deep breath. That was the toughest part. So for the matching time, if we ignore this step 2, we can get along with log m time and linear work if you do all the details correctly. All right. A brief remark on how you can compute the witnesses. I essentially said this already, and I don't want to give more details than what's written on the slide. You can do something like the KMP failure array computation and augment it so that it computes those witnesses, but we won't discuss the details. And in parallel, you can do this log squared m time. You can actually do it even faster using an even more sophisticated technique. You can safely ignore this for the class. What I want you to take from this second part is you can do a lot of tricks on parallel machines to go beyond the trivial part, the embarrassingly parallel. If you work a little harder on the problem, you can get substantial speed ups. And some of those algorithms are also implementable and practical. I'm not sure about this one, but all right, it's a theoretical result. It turns out this order log m is the best you can do. You can prove that this is the best parallel time on our standard PRAM, the concurrent read exclusive write model. So you can't really speed up the method I've shown you by much. You just have to work on this on the pre-processing. But the matching part we already got optimal in this sense. If you go to this machine where you can write concurrently, you can play even more tricks, and you can do string matching in constant time, which sounds really magic. But that's only true for the matching part. The pre-processing still needs more time. But those results are just maybe to foster your curiosity. It's just a little bit of extra information. I don't require you to know this part. So you can do a lot of trickery in parallel algorithms, but you also get a good practical speed up already results from just a simple blocking trick exploiting embarrassingly parallel parts. As long as your pattern is not too long, that's probably the way to go. All right. That's the end of the Unit 5 already. That was a fairly short one compared to the other part. And that concludes the part on string matching where we spend time on the pattern and pre-process the pattern extensively. And what we'll talk about next is pre-processing the text. But we'll do that next time.